So, I'm going to mention some background to rational homotopy theory, about which this conference and its interactions are devoted. I wanted to thank the organizers for setting this up, and I hear you're all having a good time. I wish I were there. So in these slides, I'm going to mention just how, starting from geometry of manifolds, one got a sort of structural question which was dealt with by algebra, and then this algebra has turned out to have a life of its own, and it led into more applications to geometry. And I'm conjecturing at the very end that the main point in this algebra was the notion of homotopy, and that notion leads to a vigorous development of potential vigorous development of these infinity algebras, which go back to Jim Stasheff's thesis, A Infinity Algebras, and it just opens up a whole new sector of possibilities, and these ideas are all playing a role. So happy birthday, Jim. Happy birthday, Dennis. Thank you to the organizers. All right, so the first section I wanted to talk about is reminding you of the two ways to look at spaces. So first, we have this, think of spaces as cell complexes. We have the zero skeleton, X0, contained in the one skeleton, contained in the two skeleton, etc. And the whole space X is the union of the skeletons. And these have the property that if you smash the n-1 skeleton inside the n skeleton to a point, you just get the n cells with all their boundaries collapsed to a point, which gives you a bouquet of n spheres. And such a space, a bouquet of n spheres, has one non-zero homology group in degree n. The second way is kind of the dual way. And under this duality where homology groups and homotopy groups are interchanged, the second way, we have an inverse system. The arrows go the other way, and let's, to be precise, X0 is a single point. This is a new, it's not the same X0, X1, X2, it's another system of X's approximating X. X1 maps to X0, X2 maps to X1, and each map, when thought of as a fibration, so let's take the nth map, Xn goes to Xn-1, and let the fiber be Kn. We can convert, Sayre showed us how to convert any map into a fibration by considering paths, and you get infinite dimensional spaces, but of the same homotopy type. But the fiber is supposed to be, only have one non-zero homotopy group, again in degree n. So the space is now a sort of inverse limit rather than a union. It's an intersection or inverse limit of these approximating spaces. X1, X2, X2 has connected, it has the same pi1 as X, and it has the same pi2 as X. And then the higher homotopy groups of X2 are 0. And Xn has the same homotopy groups up to n, and the higher homotopy groups are 0. And so now, among these two ways, the type 1 is more geometric. I mean, you have a picture of what it looks like, and it's harder to describe because moving from one stage to the next involves knowing what the homotopy groups of the previous stage are to tell you how to put the cells on. So it's a more geometric description, less calculable. Type 2 is more algebraic, and it can be treated very algebraically because you can describe a fibration where the fiber has one non-zero homotopy group in terms of one cohomology class. And it's in the base is Xn-1, and it's in the n plus first cohomology of the base with coefficients in pi n of the fiber, because that's the only group that's non-zero if you were trying to construct a cross-section of this fibration. And this sequence of numbers, these sequence of cohomology classes completely describes this set of fibrations. And we avoid some difficulties by restricting to simply connected spaces, or more general versions of this called nilpotent spaces. But right now, this is very easy to understand if you suppose that not only is x connected, x0 was a point, but the x1 now is also equal to the x0. And then it starts with x2. So x2 would just be a space with only has a second homotopy group non-zero, and be like a product of CP infinities and lens spaces, infinite lens spaces. Anyway, these are infinite dimensional spaces, but they're easily described algebraically. So that's all I wanted to say about this. And now, let me say the conclusion of this is that you can now take the algebraic description of spaces and you can start manipulating it as if you were an algebraist, not a geometer. So for example, you can decide, I want to tensor the space with the rational numbers which have powers of 2 in the denominator, which has the effect of suppressing 2 torsion. Well, you can start doing that. You can just start taking all the groups that are appearing in your description and tensoring them with the ring of rational numbers with 2 powers of 2 in the denominator. And you can do that for any set of primes. This is called localization, and you can do it for all the primes, and that gives you what you would call the rational homotopy type. It's just obtained by looking at this second description, which is algebraically describable, and tensoring all the algebra with Q. So that's what I wanted to get to now. So we have a rational homotopy type. It's well understood. This was well known between 1950 and 60s. And then in the late 60s, Quillen observed that you could make a nice algebraic description of the rational homotopy type. So let's go on to the next slide. The second slide discuss the relationship to closed manifolds, and again we'll simplify matters by assuming simply connected. The first major thing to notice is Poincare duality that says the Bethe numbers in complementary dimensions, let's suppose the ambient dimension is d, are equal, and in fact the torsion in ambient dimensions less 1 are canonically identified. And one writes this elegantly now as h lower I is isomorphic to h upper d minus I. So notice, if we're simply connected, Poincare duality says that things only start to get interesting in dimension 4. Before that, being simply connected and satisfying Poincare duality with respect to dimensions 1, 2, and 3 implies that you are a sphere. The manifold is a sphere. And then in dimension 4, you have the middle dimension 2, which can be non-trivial. It will be, you'll have a quadratic form of intersection there, which is the manifestation of Poincare duality. And then as the dimension goes up, the complexity of the homotopy type grows with the dimension, but intuitively it grows like 1/2 the dimension because of Poincare duality. The lower half determines the upper half, and there are precise statements to this effect, differing by 1 from what I'm literally saying. Then, dimension 4 is special now in what precedes. First of all, it was J.C. Whitehead, who observed this fact: the quadratic form of intersection of two-dimensional homology classes completely determines the homotopy type. And intuitively, you're looking at pi3 of a bouquet of 2 spheres. So you're kind of using the description 1 from the previous slide, and you're seeing how to attach that 4-dimensional cell by the 3-sphere boundary, and it turns out the quadratic form is exactly the information, and then that leads to this statement that the homotopy type is determined by the quadratic form. That's J.H.C. Whitehead back in the 40s, I would say. Now, just I wanted to mention, dimension 4 is still a current hot topic. Let's see. In the 80s, 2 of Fields medals were awarded for work in dimension 4. First, Friedman showed that all of these quadratic forms actually occur for topological form manifolds. And at the same time, within months, Donaldson and another continent showed that for smooth manifolds, there are very strong conditions on the quadratic form. But, and also, his theory implied that there could be infinitely many different smooth manifolds with a given quadratic form. Whereas Friedman had showed that all of his topological manifolds that realize the quadratic form are essentially unique. There could be a factor of 2. So it's still being discussed for manifolds. It's not known, for example, whether the smooth 4-sphere with the quadratic form is 0 is unique. So it's not known how the smooth structure is determined by the known invariants, even the fancy ones due to Donaldson. So let's go on from dimension 4. That was in the 80s. Let's go back to the 60s again. For D equals 5, 6, and 7, everything except dimension 4, and 1, 2, and 3 I've mentioned don't give interesting examples beyond spheres. Browder, who was my PhD advisor, added to the work of Novikov in the early middle 60s, who himself added to the work of Milner on his exotic spheres. And Milner was adding to the work of Thom and Smale. Anyway, all this work culminated in Browder, who put it all together and then added one crucial definition, which is the idea of a homotopy type satisfying Poincare duality. So he just took item 1 up there, took a homotopy type, added that hypothesis to the homotopy type, and called that a Poincare duality homotopy type. And then he proceeded to construct a theory about which homotopy types like that contain smooth manifolds and how to classify all the smooth manifolds. And at the end of the day, there was a purely homotopy theoretical description of all manifolds of dimensions 5, 6, and 7 in terms of the Poincare duality homotopy type and further stable homotopy invariants, i.e. of a generalized cohomology nature, like ordinary cohomology, K-theory, stable homotopy. These are various examples. This is about reformulating the work of Browder, Milner, Novikov, Thom, classifying and constructing all manifolds in dimensions 5, 6, 7 in terms of the homotopy type underlying the manifold and some further stable homotopy invariances, which are like invariants in cohomology or K-theory, generalized cohomology theories, whatever that theory was. So in this reformulation, which is discussed in my thesis, 1966, at Princeton, under Bill Browder, let's define the manifold structures on a homotopy type X to be a pair consisting of a closed manifold, simply connected, smooth, and a homotopy equivalence given F between the manifold and X. And 2 such pairs, M, M prime, F, and G, homotopy equivalences to X, are equivalent manifold structures on X, if and only if there is a smooth equivalence, i.e. a diffeomorphism H between M and M prime that makes the obvious diagram written there homotopy commutative. This is just like, motivated to make this definition. from the theory of Riemann surfaces, Teichmuller theory and the Riemann moduli space theory. It's the same thing. You have a Riemann surface M and a homotopy equivalence to a fixed topological surface, and then you say two such Riemann surface structures on the topological surface are equivalent if there's a holomorphic diffeomorphism between the two Riemann surfaces that makes the diagram homotopy commutative. Then this is an uncountable set. It has moduli, and it forms a space called the Teichmuller space. And then you process this space in what I'm going to say next to produce the quotient Riemann moduli space. So we'll do the same thing. So let's note, but now everything is, there are no moduli in topology. You know, two very nearby manifolds are actually diffeomorphic. You can't vary them continuously. So note that the automorphism of X, aut X, which by definition is the set of homotopy equivalences of X defined up to homotopy, and these form a group. And this group acts on this structure set, the set of equivalence classes of manifold structures on X, and the set of orbits of this action. This means, or it's just really all the different manifolds up to diffeomorphism which have this homotopy type equivalent to X. So it's a different set than the set of manifold structures. And in the thesis, what could be done is one could calculate this set, and it was a torsor of a finitely generated abelian group. Torsor means it's a set on which a finitely generated abelian group acts by translation with one orbit. And this finitely generated abelian group was, its rank was the sum of the Betti numbers 4, 8, 12, etc., not counting the top. And the torsion was a complicated object which Milner had studied. Milner and Kavere had studied in terms of the exotic structures, exotic differential structures on spheres, and these are somehow all combined in various dimensions and put together to figure out what this torsion is. Plus there's another phenomenon. Anyway, without going into that now, which is very interesting, by the way, I recommend reading the paper by Milner and Kavere from the 60s, which is the only paper I read when I was a graduate student, line by line. It's a masterful piece of work, a masterpiece. Anyway, we get down to the problem. This is, we can reformulate this Browder-Novikov theory in terms of this manifold structure set, and we can calculate the manifold structure set, but we have to, it's calculated relative to giving the homotopy type. And then we also have the automorphism group of the homotopy type. So we're now down to two problems of understanding. What is the nature of a homotopy type as a mathematical object? I mean, what kind of thing is it? How do we understand it? Well, it's some kind of algebra I've indicated in the first slide. But what kind of algebra is it exactly? And then furthermore, this group is, this non-abelian group, the automorphism group of the homotopy type, is acting on the structure set, and the set of orbits is really what you want to understand. What are all the manifolds of a given homotopy type? Is there additional structure on this set of orbits? And in order to determine that, is there additional structure on this group, automorphism X, and how it acts on this set of manifold structures? So this brings us to the next slide. Let me, in this fourth slide, let me do a little example to illustrate some of the previous remarks so you get a flavor for what's going on. So I'm going to take my homotopy type, simply connect homotopy type, to start with two 2 cells, a bouquet of two 2 spheres, and then I attach one 4 cell by a map of its boundary to the 3 sphere into the 2 skeleton, and that will be an element pi3 of S2 wedge S2. in these low dimensions, we can compute these things. And we can't so easily in higher dimensions. That's why the other picture is better for doing algebra. So, so the homotopy group now is 3 Z's. And a picture of these 3 Z's is the following. Take the preimage of a point in one sphere and also at the same time the preimage of a point in the other sphere, general points. The preimage of disjoint sets is disjoint. If you don't know that, that's a good thing to learn. And the preimage of one of the points is generic, typically would be a 1 manifold. So I'm imagining it to be a circle, each one to be a circle. So I have a picture on the right. I have 2 circles, and they're linked somehow. And then there are vectors on them, and those vectors come from choosing at each of the points a tangent vector to the sphere and pull back that tangent vector to get normal vector fields along the preimage of the points. And then we can compute a winding number for each vector field around its circle. That's give us the diagonal entries L11 and L22 of the matrix, and then we have the mutual linking number L12 between the 2 curves. These require orientations and everything. I won't go into that now. And the simplified example is to just take 1,2 sphere and attach a force L, and then you would just have one self-linking number L. Now, what are the homotopy types of these spaces? Well, remember, we can localize homotopy types. And when you have quadratic forms floating around like these matrices define quadratic forms, the prime 2 behaves differently from the odd primes. It's a little more tricky. Like you get a Z mod P for an odd prime somewhere, and you get maybe a Z mod 8 at the prime 2 or a Z mod 4 instead of just a Z mod 2. Anyway, in the simplified example, the homotopy type we'll compute the homotopy types over Z and over Q. And for both examples is a simple statement. The bilinear form defined by the matrix, the 2 by 2 matrix or the 1 by 1 matrix, over Z or over Q determines the homotopy type over Z, the ordinary homotopy type, or after we've localized to Q to invert all the primes, the rational homotopy type, as indicated in the first slide how that would be defined. Now let's do some calculations. First, I want to compute the homotopy type over Z and over Q in the simpler example. And there we just see that the absolute value of that integer is a complete invariant of the integral homotopy type. But when we take because we can change the orientation of the top cell to plus or minus, and then that would change 1 lambda to minus lambda. So just the absolute value is an invariant. But over Q, when we localize the homotopy type, now all the units in Q can be used to change the generator of the top cell. And so we have to be able to change the lambda, which could be any non-zero element in Q star, and Q, we'll call Q star, and then we could change by squares the orientation. And so it's Q star, the non-zero elements of Q, the multiplicative group, modulo the even elements, or the ones with square roots. So it's, Q star is interesting as a group. It's the free abelian group generated by the primes. You think of a rational as numerator and denominator, you've got a bunch of primes, and either they have positive or negative exponents, you get the coefficients of a free abelian group. And then you divide by the squares, all those things have to be even, so you're left with countably many Z2s. So already the classification of the integral and rational homotopy type in this simple example shows some interesting structure. Now I'm just going to give the answer for the more complicated homotopy type and what its automorphism group is. So the automorphism group, so now the rational homotopy type comes in to help the story, because basically the automorphism group is the automorphism group of the quadratic form. either over Z or over Q. So over Q, it consists of 2 by 2 matrices over Q, which preserve the quadratic form, which is the linking form, L. I've indicated L, and so that's an algebraic equation among the entries of M. Because that transpose is there, you could put it on the other side, and anyway, you get a nonlinear equation. And then the automorphism group of the integral homotopy type turns out to be the integer matrices that satisfy the equations of the automorphism group of the homotopy type. So a lesson here is that the integral homotopy types collapse together quite a bit to the rational homotopy types. The rational homotopy types are still quite rich, but then the automorphism group up to a finite, there's a little word commensurable there. So the automorphism group isn't really that integer matrices, but it's commensurable to the integer matrices, which means that there's subgroups of finite index in each that are isomorphic. Anyway, so the automorphism type is tightly controlled up to finite considerations by the automorphism of the rational homotopy type. Some of you may have noticed that I wrote the equation on the matrix M of defining the automorphism of the homotopy type as a linear equation, and it can't be a linear equation because it's defining kind of a number theoretic analog of the orthogonal group. The correct equation is the matrix M transposed in the usual sense, composed with L, and then composed with M again, is the matrix L. So this is n squared quadratic equations whose coefficients are in L, and this defines what's called an algebraic group, and in this case it's defined over Z or over Q. You usually go to the smallest field containing the coefficient ring in question. So raise the question, what is the nature of the homotopy type? What is the nature of the automorphism group of the homotopy type? What is the nature of its action on the manifold structure set? And what can we deduce from this structure? So the example suggested the following theorem would be true. That the automorphism group of a finite simply connected homotopy type is commensural. That means two groups are commensural, meaning subgroups of finite index. There are subgroups of finite index in each that are isomorphic, co-measurable. So odd x is commensurable to the integral points, the z points of an algebraic matrix group defined over the rational field. So before it was the quadratic form, the orthogonal group of the quadratic form determined by the linking matrix. And the second part of the theorem is that not only is the group abstractly algebraic, the way it acts on the algebraic topology, in particular on the set I'm interested in, which is the structure set of manifold structures on a homotopy type, which we've said is described by stable homotopy theory, some generalized cohomology theories, and so on. The action of odd x on that for a Poincare duality homotopy type is a Q algebraic matrix representation. That means that it's really given by a homomorphism of the algebraic group into the group of matrices, a linear representation, so-called. Now, and so our example suggested this theorem, and the action of the automorphism group on the homotopy type was acting through its algebraic topology. Now, so one corollary, this is something I was worried about. If you took the example, you can have an example of the free group on two generators. Free group is basically 2 by 2 integer matrices, determinant 1. And you can have it shearing in one direction in 3 space and the one generator shearing in one direction, the other generator shearing in an orthogonal direction, and that'll be a matrix representation. The kernel of that, because two shears commute, will be the commutator subgroup of the free group on two generators, which will be infinitely generated group. So that representation at the integer level cannot be defined algebraically in terms of matrices over the rational fields by algebraic linear representation, because it's known that the arithmetic groups, the integer points in algebraic groups are finitely presented groups. One finds fundamental domains and analyzes, that's a whole endeavor. And so a corollary of this theorem is that, first of all, ought x itself is a finitely presented group. It's an arithmetic group, being the integral points, etc. And secondly, the subgroup fixing a set of cohomology classes is also an arithmetic group. It's the arithmetic points inside the algebraic group defined by fixing a vector in an algebraic representation or a set of vectors. And so it'll be a finitely presented group and have all this nice tight structure. And the example I'm thinking of is when you go back to the structure set, you have the structure set on the homotopy type. It's a torsor of this finitely generated abelian group. We know what the abelian group is, and we know it's really up to torsion. It's just the direct sum of the torsion-free part of the 4th, 8th, 12th, etc. cohomology groups. And the manifold picks out elements in those groups, namely the Pontryagin classes. And one would want to study the diffeomorphisms of the manifold, and then these would have to fix these would be elements, homotopy equivalences that would fix the Pontryagin classes. And so this corollary applies to say, well, at least those are nice arithmetic groups, and one can continue to analyze things in that vein. And the workhorse lemma of this subject, this tool, this is a very powerful tool. And remember from the previous example, it's not so trivial to go between the integral story and the rational story. We got this, Q star mod Q star squared and the primes coming in. It's not so trivial to go between the Q and the Z stories. And the bridge is provided by this arithmetic group statement, because an algebraic representation, suppose you have an algebraic representation that you're studying, like you're proving something, like you're moving up through the second decomposition of the space, proving things by induction. Then you're going to have to prove something good at the n-1 stage. Then you have to pass to the nth stage. Well, you have to fix that twisting class that we talked about in the first thing, the obstruction class. So that'll be passing to a stabilizer. Then we'll have to make a lifting of that to the next stage. That'll involve extending by some kind of abelian group. And we have to stay in this context of Q algebraic groups, and then we continue on with the induction. So, like, for example, suppose you want to prove diffeomorphism group is an arithmetic group, but you would proceed through the stages, you'd fix the Pontryagin classes, and go up through the stages, and you could succeed because of the following theorem, that when you have a homomorphism of Q algebraic groups that is as a map of Lie groups, just when you look at the C points or the R points, it's a surjection at that level, but it's defined over the rationals. Then the induced map on the integral points is an almost surjection in the sense that the image will be a subgroup commensurable to the whole group. So it's like if you can solve a bunch of integral linear equations, they're solved for you exactly up to finite possibilities. So it's a powerful machinery that was developed by Burrell and Harshchandra. Well, getting back to the subject of this meeting, rational homotopy theory. So the way the previous theorem was proven was to, or was investigated, was to look into Quillen's paper, which is a masterpiece, and even today it's the best source, where he showed there is some algebraic category which is equivalent to the rational homotopy category. In fact, he had 3 versions: completed Hopf algebras, differential Lie algebras, and differential coalgebras. And then this is 1968, and then I observed around 1970 when these questions were arose about manifold structures for me, that one could understand the structure of homotopy types as in description 2, tensor Q, as iterated algebra extensions of free differential graded algebras using Q polynomial differential forms. And this, as I learned more about this, I realized that I learned about these differential forms from Whitney's book, 1957, and as I was writing these things up and so on, I realized that it was pretty well known during the 50s. Tom has a Bourbaki seminar discussing description 2 in a certain way, and it had sort of been forgotten because of the emphasis on torsion, which is the crucial part of the manifold structure set. If you fix the homotopy type, the rest is just something very clear-cut, except for the torsion. So there was a big emphasis on that. But if you want to study the homotopy type itself, it's a very nonlinear problem over Q, and so it has a deeper structure, which is quite interesting. So this was, in a way, the only original aspect of my paper was to think about the current problems and say, hey, the rational story is actually quite interesting. And then doing it with differential forms ties it up with manifolds, obviously, because this algebra, when you can go from Q to R, or from Q to C, and then work with smooth or even holomorphic forms on real or complex manifolds, and then all that rational discussion fits with differential geometric ideas. So this extends the scope of these algebraic methods into differential geometry, or extends it further into differential geometry. And now, I wanted to emphasize that the difficulty in developing the theory, there was a difficulty. It wasn't just, and it wasn't just putting together things exactly, because the difficulty was handled in one way in Quillen's paper by redefining the whole idea of a model category. That's how he dealt with it. And I didn't understand any of that at the time. And the way I dealt with it is to explicitly define the notion of homotopy between maps. And a lot of explicit definitions that all turn out to be equivalent. The guiding idea was to think of the obstructions to a homotopy and where do they live. It's a cohomology in a certain homotopy group, and you understand in terms of the algebraic picture both of these things, and then if your notion of homotopy consistent with that obstruction theory, you have the right one. And the very explicit notions are quite useful. This aspect of the story extends into modern developments starting in the 90s to study more general algebraic structures, infinity versions of very general algebraic structures. When these include algebras over operads, properads, and props, and TQFTs, and so on. And the idea is to apply the method not to the algebras themselves, but to the definitions of the algebraic structure, to the TQFT or the props. because these are some kind of generalized algebras. And I think that's kind of the wave of the future for these ideas.